Welcome back, everybody. Today we're going to be stepping into Chapter 9 and starting to think about these things called differential equations. These are used to describe how quantities change in all sorts of different contexts. And so today we're going to get a feel for what these are, what they look like, start to see a way that we can feel out somehow what solutions to these equations look like, and also see how we can algebraically check that a function is a solution to a differential equation. So let's dive in and start at the beginning with our basic definition. So a differential equation is first and foremost an equation. It is a relationship that a function has with its derivatives and input variable. And so the fact that we have derivatives involved, that's what makes this a differential equation. And this could be first, second, third, fourth, however many derivatives. And our input variable, sometimes we write it as x, sometimes it's t. But this is what it is. It's some sort of relationship. It's an equation. And so it might look like one of these three. Up at the top, we can imagine these m, c, and k are all different numbers. It turns out that in this situation, that this equation actually describes the motion of a spring. Like, not a spring of water, but a coiled up spring. In the presence of what are called damping forces that look to kind of slow it down. The second differential equation down here, here we're imagining that this little k and this big M are numbers. It turns out that this equation comes up thinking about population growth. In the specific case, where our population is growing, where it can't grow like without bounds, something is in the environment that kind of puts a cap on the population. So somehow with a max population, or carrying capacity it's called. Down here, this third equation is the first one actually of these three where the input variable x has showed up. And interestingly, this differential equation is just a random differential equation that I made up. Right? It doesn't have to come from some physical context. It can literally just be some equation that we imagine and think up and write down that involves our function. So we're imagining that y stands for some function, its derivatives, and maybe its input variable as well. Now, there's a little bit of terminology when we first step into this world that I want to introduce us to. The first is a useful way of looking to kind of classify differential equations. It's somehow similar to the degree of a polynomial, right? We'd say that the degree of a polynomial is 2 if the highest power of x that showed up was 2. If we had like 3x squared, I don't know, minus x plus 5, right? We'd look over here and say, this polynomial is degree 2. Well, with a differential equation, we do something similar, except we look for the highest derivative that's involved. And in our first differential equation, it's the second derivative that's the highest. And so because of that, we say that our differential equation has order 2. So the order of a differential equation is just the highest derivative that is involved with it. And so our middle and bottom differential equations here, these would both have order 1. Now we have an equation, and when we have equations, we want to find solutions to these. And what that means for a differential equation is finding a function. So a solution to a differential equation is a function, such that that function satisfies our differential equation for all x, perhaps in some restricted interval that we are looking at. And so to give a little picture of what that could look like, we're imagining that if we have a particular function, y of x, well, this y of x function would be a solution to a differential equation if at every single x in some interval, let's just say we're looking at all x's on the x-axis, if at every single x, if we take all of the function information we have at that point, it satisfies our differential equation. And so, for example, let's just maybe keep in mind, just as something to think about, we had our made-up differential equation, 3y prime minus y equals 2xy. So if we think about this particular x here, well, we get a point on our graph, right? So we get a y along with our x. So we have an x and y, and so we could plug that in, for the x and for the y here and here, right? But we also need y prime information, and so that would be geometrically coming from the slope of the tangent line here. That's supposed to go through that point. And so here's the tangent line, and its slope is y prime at that particular x. Right? And once we have that on hand, we could plug that in for y prime. Right? And at this particular point, we could figure out y double prime and y triple prime, if our differential equation called for it. And if this function is going to be a solution to our differential equation, well then, in particular, at this x right here, if we take all of our function information, x, y prime, and plug them in, we have to get a true equation. Right? The left-hand side has to equal the right-hand side. And that's going to have to be the case, right, as we plug in all of these different x's and look at all these different points along our graph, if our function is going to be a true solution to our differential equation. And so with that in mind, and with this picture in front of us, let's take a second to ponder these ideas with this question. Could this curve, this function, be a solution to the differential equation y prime equals 1/2 y? Pause the video, think about this for a little bit, think about why or why not, and we'll chat about it in just a sec. All right, well, there's a number of different ways that we could see what's going on here, but the short answer is no. Our curve here could not be a solution to our differential equation. One way to see why not is if we look at our curve here. There's a lot of parts of our curve above the x-axis, right, with positive y's. And if you look at our differential equation says, well, our y prime, our slope of the tangent, is always 1/2 of our y. And so, well, if y is positive, our differential equation says that y prime is 1/2 of that positive number, which is still positive. But if we look up on our curve, in fact, here's a point on our curve where y is positive, but if we look at the slope of the tangent line, y prime is negative. And so that is one way to see that now this particular function here could not be a solution to this differential equation. There are others as well, and you might have thought of one. But an interesting thing about a differential equation like this is we can actually try and make more precise this idea that we can use our differential equation to tell us what our y prime has to be, what our slope of the tangent line has to look like. We did a little thinking about that here when we said that if y is positive, y prime has to be positive. But let's see if we can be even more precise than that. So we can see what the slopes of a solution function would have to look like by looking at this requirement on our y prime. And so let's think about this. Up here, I have kind of some points picked out. Up here at this point, what is that? That is 3, 2. Well, if we have a solution function to our differential equation that passes through this point right here, 3, 2, I claim we know exactly what the slope would have to be there, right? If we took our x and y information and plug it in to the right-hand side of our equation, in this case, we really only need our y. Well, what do we get? We get that y prime would need to equal 1/2 times 2, which is 1. And so, whatever our solution function is, we don't know its true identity, but we know what its slope at this point would have to be. Its slope would have to be 1. And so to represent that, we can draw just a little chunk of a line segment, a little chunk of a tangent line if you'd like, with that slope 1 at that point. And so this just represents the slope that a solution function would have to have going through this point. Right, and we can do this for other points as well. Down here, we have the point 3, 1. What would the slope have to be there? Well, from a differential equation, the slope would have to be 1/2 times 1, which is 1/2. And so we can draw a little chunk of a tangent line here, and we can try and represent the slope of 1/2 just roughly by making this tangent line just a little bit more mellow than the one above it with slope 1. There we go. That looks reasonable. All right, and similarly, if we plugged in this point here, 3, 0, well then y prime would be 1/2 times 0, which is 0, and so we'd actually have a horizontal tangent line there. Down here at 3 minus 1, y prime would have to be 1/2 times minus 1, which is negative 1/2. And so we actually would have a negative slope there. Up here at 3, 3, going to have a slope of 1.5. It's going to have to be. So we make it just a little bit steeper than our slope of 1 that we drew right below. And we can start to see, at least for these points, what our slope would have to be. And we can imagine perhaps that these points are not somehow special. We could pick any point in the plane, and through our differential equation, see what the slope there would have to be for a solution function. One of the things that's nice is that our differential equation, y prime equals 1/2 y, actually does not involve x at all. We say that it is autonomous since it doesn't involve the input variable. And what's kind of cool is that the slope then here that we saw at our point 3,2, well, if we checked out the point 2,2, right, change the x, that's not going to change our slope computation at all. We're still going to see that exact same slope of 1. And so we can try and draw that in with the same slope of the one right there. And similarly, this point, any point here with the same y value is going to have the same slope as our point over here, 3,2. Right, these are all going to have slope 1, so we can try and draw those in. All right, and similarly, all these points down here with the y value 1, those are all going to have slope positive 1/2, and so we can try and draw those little line segments in with the right slope. And so autonomous differential equations kind of have this nice property that once you know the slope at one point, you need to kind of spread that left and right as much as you'd like because it doesn't depend on the x. Now, you can imagine doing this for all sorts of other points. Any point in the plane would work. We can get a little chunk of the tangent line there. What we're building here is called the direction field for our differential equation. And there's a nice interactive through Desmos where we can actually see this a little bit more completely. So if I bring that up here, we have our differential equation, y prime equals 1/2 y. And so here we can see a more complete picture of the direction field. And here we can actually slide a point around and see at that point, what the slope would have to be through our differential equation. And the idea is that a solution to our differential equation is going to have the appropriate slope at each and every point. And so a solution curve is somehow going to move through our direction field perfectly, at each and every point matching the slope that it's supposed to have. So we can kind of see that it would be like starting to curve up. If we had a solution curve up here with positive y's, maybe down here for negative y's, it would have to do something like this, kind of start pulling down if we're going to move through these this direction field, perfectly. And we can get an even more complete picture of what's going on here with another interactive. So here we have our same differential equation, y over 2. Here now we've chosen the particular point, and here we can see actually what a solution curve would look like, and we can see that indeed it is, kind of following the instructions of our direction field and matching the slopes as it should. One of the things that we can see here is by dragging this around, we get different solution curves, all moving through the direction field perfectly. And so in general, a differential equation actually will have infinitely many solutions. And sometimes we want to find a particular solution, that goes through a particular point. Like we really want it to go through the point 3, 1.42, like we have here. In that situation, we say that we're solving an initial value problem, trying to find a solution to a differential equation that goes through a particular point. Maybe just for fun, before moving on, with this interactive, we can toss in some other stuff and change our differential equation with our, if I make it y times x over 2, we get a new direction field. And again, the idea is that our solution curves to this differential equation are going to be moving through this perfectly. And if we toss in a solution curve, we can move our initial condition around at this point that we're asking to go through and see what those solution curves would look like. And so here, this little interactive doesn't know exactly what these curves are. It's using some approximation techniques to get a sketch of the curves graph. Now that's the idea. All right, moving back to the notes. Yeah, so as we said, finding a solution to a differential equation that goes through a particular point, in the interactive it was that red point we were looking at, is called solving an initial value problem. All right. And so that's the geometric idea of a differential equation, what solutions look like. But how can we actually check things algebraically? If we have a particular function, y of x, on hand, how can we show that it's a solution, without kind of sketching a graph and seeing if it seems reasonable, actually truly algebraically show this? Well, a differential equation is an equation. And so we can show that a function solves it like we would any other equation. We just need to plug in and check that our left-hand side and right-hand side match up and equal each other. So with that in mind, why don't you take a minute and check out the members of this family. And I'm calling this a family because this C up here is just some unchosen constant. But here we have a family of functions. Why don't you take a moment, pause the video, and show that it's a solution to this differential equation by plugging in on the left-hand side what we need to, and on the right-hand side what we need to, doing a little algebra work and showing that these match up. All right, well, let's talk through this together. On the left-hand side, to plug in, right, we just need our x, so there's nothing to do there. And we need the derivative of our function y. And so we got a little bit of prep work to do here before we can plug in. And so to take the derivative of our function y, here I've moved the x up to the numerator and taking the derivative there and doing a little bit of exponent simplification. 1 plus c over x squared is what the derivative of our function looks like. And so it's this 1 plus c over x squared that we take and just plop in where we see y prime. Doing that, and then just taking our x and distributing it across, we get some cancellation on the right, and we're left with what we see here. So that's what the left-hand side becomes. Now we just got to look at the right-hand side and see that it matches. If we do that, right, we don't need to do anything for the x, that's just our input variable, but we do need to just pop the y in where it goes. And so our y comes right here from our function definition. And so we'll just take that and pop that in where we see y here. Doing that, and now doing a little distributing the negative, we get 2x minus x, which is x, and the dust settles here. And our big observation is that, hey, that's the same thing as we ended up with the left-hand side. And so since our left-hand side equals our right-hand side, our function here, which represents a family of functions, is a solution to our differential equation. Now, we mentioned a few minutes ago that sometimes we want to find a particular solution that passes through a point. Let's look at an example of that where we just use our same differential equation that we've been playing with here. All right, so this is the same differential equation as we were just working with. Let's solve the initial value problem with that differential equation and this initial condition, it's called. And so the language here of solve the initial value problem means we want to find a solution to the differential equation that also satisfies y of 2 equal 3. And this is another way of phrasing the fact that our solution curve passes through the point 2, 3. Well, with our work just a few moments ago, we found a family of functions that solves our differential equation. And so in order to solve our initial value problem, we just need to figure out which one of those functions satisfies our initial condition. And in other words, which one of these functions works is equivalent to finding the particular c that makes that happen. So why don't you pause the video, see if you can determine which one of these functions, which c do we need in order to have our initial condition satisfied. All right, so how this can go is actually just by taking our initial condition and plugging in on the left-hand side, right? For our function to satisfy y of 2 to equal 3, well, we need it to be true that if we take our function, this one right here, and we plug in 2 for x, that what we end up with is 3. And so taking this left-hand side y of 2 and writing what that is through our function, it's going to be 2 minus c over 2. Now we have an equation that just involves our constant c that we want to find and some numbers, and so we can just solve this for c, right? Subtract the 2 over, multiplied by -2. Looks like the c that's going to work is -2. And so popping that in there for our c up in the numerator, we find the particular function from that family of functions that satisfies the initial condition and thus solves our initial value problem. Well, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.